Good, we've discussed the problem statement and now we will carry out the questions. Sorry, in the previous video I forgot to include this. This table was also provided with the question to give us the very specific detailed category of the applicable weld. But we will discuss it in detail a little bit further. Our first question is, what is the partial factor for fatigue for this problem? Let's just make it partial factor for fatigue. Now, as you can remember, right in the beginning of the course, I introduced you, and I'll open my slide to this slide. To this slide where we spoke about the partial factor for fatigue for different assessment method and consequences of failure. In this case, we had if I remember the question correctly, but I can reopen it, we can go back to the question. The question in this case said, safe life assessment method with high consequence of failure. So what I'm going to do is I'm going to copy this table to my assignment, to my table where I perform the calculations, which is this one, and Alt-C, Control-V, and as we say, for a design philosophy of safe life assessment method with high consequence of failure, the partial factor for fatigue is now, if we look at the table, and let's just insert lines so that we can see what we do. What do we say? We say we have a safe life method, so there's our safe life method. Right, and let's use a little block because that always looks a little bit better. So we have the safe life method that we want to use, and I'm just going to make this block red so that we never forget about the line and we can clearly see it. And I will just make it so that we're going to use it quite a lot of time in this example. So let's just make it the default shape. So that's our safe life method, and they say high consequence of failure, and you can clearly see from this gamma MF is Alt-EI gamma MF in this case is equal to 1.35, and that we get that from the table below. Let's see what the second question is. The second question is, what other factors need to be taken into account in this problem? Other factors, let's call them the correct name, influencing factors to take into account. Now, what's very important is that there was not a lot of information given to us so that we can see what are applicable. For example, there were no post-weld improvements done to the weld in this case. If there were, we would have added the applicable benefit factors. However, in this case, they say that the specimen is operated at a temperature of 250 degrees Celsius. Now what I'm going to do is I'm going back to my slides, and we are going to look for the benefit factor for temperature. So I'm going to page down and see when I get to the effect for temperature. These were the slides that we discussed in class. And there we see the effect of temperature, and what we can see according to the rule, and I will copy this graph, is that the characteristic strength at the elevated temperature, at the high temperature, is equal to the original characteristic strength times EHD divided the value by at 20 degrees, because that's what we have from the table. I'm just going to pause quickly. Good. So what we're going to do now is we are going to copy this graph, this curve, into the report, so that you can see what the temperature effect is that we need to take into consideration. They say here that we're operating at a temperature of 250 degrees Celsius. So we go up to 250 degrees Celsius, right to that point there. Let's make the arrow a little bit darker. Let's make it red so that it stands out a little bit. And let's close this here. And from this we can see that the affecting factor for temperature works out approximately 0.9. At this temperature of 250 degrees Celsius, we sit with 0.9, and that's the... So what we have here is the new characteristic strength for the temperature compensated application is, and now we know the new delta sigma C that we need to work with at the elevated temperature, let's call it C, L high temperature, which is equal to the original delta sigma C that we had, the original characteristic strength that we had, divided, of course, by gamma MF, because we still need to, and multiply by the factor that we see below, which is 0.9. Right, because that's the reduction factor that we have for temperature. Let's see what the next question is. The other factor that we need to take into consideration, if we look at the specimen here, we can see that the detailed category that we're talking about here is probably this one here, because it's full cross-section butt welds. Let's see about the grinding that we have here, the height of the convexity. Okay, we have run-on and run-off pieces, welded from both sides, but note the difference between these two. This one is all welds ground flush to the plate, so that's not what we have. So we do have a temperature effect, a size effect for thickness more than 25 millimeters. So that's the other one that I'm going to include, and I'm just going to include it there. And we can see it's 25 divided by T, it's 0.2. So I'm going to say in this case, the other one that we have, other influencing factor that we have, and I'm going to make this a little bit smaller, we can still read, is alto AC. Let's call it the size effect. And let's just make it yellow so that we can see here. So in this case, the factor for size in this case is, and K size, small k, K size, in this case is, I'm sorry for that, alt mu EI, let's put an equation in. K size is equal to, of course, we've got two answers, so I'm going to give it in matrix form, and the one is 1, and that is, of course, for T smaller or equal to 25 millimeter. Then for T larger than 25 millimeter, according to the equation above, it's equal to 25 divided by T, the thickness, to the power 0.2. So that's what they say the value is. So I can add a little bracket here to the left to just make it look fine. So that is the size effect that we need to model. Because we had both here, let's just make this one temperature. And I'm not going to add any other effects because there are not any other effects applicable in this case. Right? So there we have 25 over t to the power 0.2. And those are the two effects that I see applicable in this case. There's nothing about grinding and burring that can add a benefit. Wait a minute, they did say something about grinding. Let's see. The height of the weld, a smooth transition to the plate, that's what we have in any case. Run of pieces subsequently. Plate edges to be ground flush, and it's welded from both sides. But they did say something in the question. They said the height of the weld convexity is measured at 8% of the weld width. The smooth transition to the plate surface, that's what we have. The welding process can run on and run off. The edges ground flush in the direction. So yes, we don't have any additional effects to consider in this case. So those are the only two influencing factors that we have. Let's go back to the question bank. What is the detail category for this joint? And what value must you take into account for the thickness effect in this case? Now let's go look at the detail category. Detail category, we've seen, if we look at this table, we've seen that the detail category is 90 here, because we've already read the detail here, and that covers this specific joint. So I'm going to grab this specific section, and we're going to say our detail category for this joint, right? So let's make it like this, detail category. And then what we can say is Alt-AC Control V. We can say, let's put this on a new page, so that it's very nice and detailed. We can say, based on the information supplied, the detail category for this joint is 90. Right. That is also the characteristic strength at 2 million cycles for the original joint. That means without any modification effect. As we can see, we need to model the thickness effect. In this case, they said the thickness of this problem is 28.95 millimeter, the thicker part that we're talking about there. So let's go down here. We need to take that into consideration. We just see here quickly. The weld is expected to, the weld will crack in the thinner part because, of course, the stresses are less on that side. So in this case, we don't have a thickness effect because we only have 20 millimeters here. So we can say in this case, there is no thickness effect need to be taken into consideration. And I will motivate why. No thickness effect need to be included because the crack is expected to initiate in the thinner section, which is 20 millimeter in thickness. We don't expect it to initiate in the thicker part, so no thickness effect needs to be taken into consideration. Let's go and look at the next question. The next question is, where do you expect the crack to initiate in this joint? In this case, we expect the crack to initiate at the weld toe on the thinner section. At the weld toe on the thinner section. So we're going to say point of crack initiation. And we say initiation. Sorry, my spelling error is, I see, Control UB. The crack is expected to initiate at the weld toe in the thinner 20 millimeter plate. Good. In the next video, we are now going to do damage calculations based on the information given to us. We will first compile the SN curve, which is what I'm going to do in the next presentation, to derive an equation for the SN curve that we need to use in this case.